Hello, this is a video about the Qibec 1-bit 1-instruction transistor CPU that you can see right here. In this video we'll take a look at the physical appearance of the CPU, in other words this box that you see right here, this baseboard plus plug-in modules. What do they do? And without going into too much detail, because the functionality of each plug-in module is described each in their own video, we'll take a look at how the logical model of this CPU, so the block model, corresponds to the position of each board within the baseboard, and what the baseboard looks like, and so on. Right? So first of all, this is about 20 by 20 centimeters, about 12 centimeters high or something like that. What you can see here is a acrylic fluor acrylic cover plate. That is to prevent the module from dancing around too much inside the baseboard. It's just for aesthetic appearance. This is the bare baseboard. Underside is not very interesting. Top side is not very interesting either, to be honest. What you see here are the only thing that's on the baseboard basically is filter caps for inputs. So each module has filter caps at all of its inputs, plus a buffer cap for each module to buffer the supply voltage a bit. And for the rest there's not much more. Now let's put this box aside, put this baseboard aside, draw the logical block diagram of the CPU. Once again, without going into much detail, because all this stuff, the dynamic behavior of the CPU, what each subsystem does, and how the bridge module works, how the display module works, how the software works, is all described in a separate video. How the RAM-ROM interface works is all not described here. This is just about the physical appearance, right? So let's compare. At the left, logical appearance of the CPU. In other words, we will be drawing a block diagram here, and the right is the physical appearance. Let's start with the physical. As you can see, is this one. Let's look at it from the top down. So you have a box, basically, looks like that. Lead 3D effect. You have a PC. Of course, all PCs look like this nowadays. Monitor. There you go. There's a USB cable from the PC connected to the CPU. I must say, the interface between the PC and the CPU is subject to change. So what we'll be drawing here is basically the PC and CPU interface for this version. Let's call it version 1. Right? So this is a USB cable. We won't be talking about what the PC does exactly. In short, it is emulating the RAM and the ROM and providing the control signals to the CPU, but that's subject of another video. Let's draw the logical diagram of the CPU. Let's draw the whole system. Start with a big fat CPU, like that. It talks to a ROM. How everything is connected is not subject of this video, once again. On the bottom side there's a RAM. CPU reads and writes the RAM, the ROM indexes the RAM. So, all the subsystems are once again described in another video, so we'll go through them quickly now. There's an address latch, another address latch. There's a MUX, there's an address increment unit right there. Data flows basically upwards, or the address basically flows upwards. For details about this, view another video once again. And this is a MUX, and this is a D latch, forming the interface between the CPU and the RAM. Right? So that's basically what it is. Now let's go by all the plug-in modules one by one and take them out and take a quick look at them, and then draw them in the physical in the physical diagram, so we can see how many modules on the left side, or for example, how many modules participate in forming the mux or the latch and so on, and where they are located in the physical diagram. So first of all, let's start with the address increment unit right there, +1 block. That is located right there. See, ink, that is 1/2 of the increment. Let's take it out. And the other one is right there, the other half of the increment. So now we go. So these two modules are basically sitting there and there, something like that. Alright. These are discussed in another video, but basically each form an 8-bit increment unit, and together they form a 16-bit increment unit. These are used to increment the program counter. Done. So in the logical model they are sitting here. So this +1 block consists of 2 modules, right? In parallel. Next up, multiplexer right there. If you look at where that is in the physical CPU, and that's one is there, mux 0. That's one part of the multiplexer. There's another one there, mux 1, right? Let's take that out. So we have one mux block sitting there and another one sitting there. Let's see, there's another one there, mux 2. Take that out, it's sitting there. And should be another one, mux 3 sitting there, right? So that's that, sitting right there. This will probably become a mess, but let's see. Oops, let's see where we end up. Now that went well. So now we have 4 multiplexer modules like this, all identical. These are described in a different video in detail. Now the label says 5-bit multiplexer. This could have been a 4-bit multiplexer with the same effect. Basically this set throws away 4 bits. It was a bit silly when designing this, but maybe next version I'll change it, maybe not. So together in parallel these form a 16-bit multiplexer, and we throw away 4 bits out of the combined 20, right? So that's that. So that multiplexer block consists of, is formed by 4 plug-in modules. Let's draw it like that. Next up, address latch. Now this address latch is also described in a separate video, but basically this is a two-way door. So first this latch opens, then data passes through to the middle point between the two latches, then this one closes, then this one opens, and data can pass all the way through to the program counter output of the CPU. So, even kijken. Latch. That's not exactly sure which is which, but let's draw them in. So that's sitting here and here, something like that, and latch and latch sitting there and there. Backmost modules, something like that. Now, so these are 8-bit wide each. So let's say this pair forms a 16-bit bottommost address latch right there, and this pair forms the topmost address latch right there. But it's just a matter of placing these modules in the CPU, because these are all identical, yeah? That was the whole purpose, to make a set of identical modules to make debugging easier and testing easier and so on. So now we're left, well, first let's make it clear that both halves of the address latch each consist of 2 modules. So all the blue blocks are now separate plug-in modules, right? So almost done. Now, we're not going into detail now, but these subsystems all are all activated in turn. So first one is activated and then the other one is activated during one cycle. So during each cycle you have a number of activation steps. First this, then that, then that. Next cycle again, first this, then that, then that. So to do that you have a timing module which basically emits pulses to activate also the write to the RAM to activate subsystems one at a time. So that at every moment no two subsystems are activated at the same time. Module taking care of that is this one, timing module. That's a bit complex, well, as far as complexity goes in the CPU, and it's also subject to another video. So we'll not discuss that in detail, but it's this module basically, right? Toss that away, and that module is sitting there. We'll give it another color because it's a bit special, right? Now, as you can see, there's two modules left, one on the front, one on the back. One on the front is, part of it is the DIO latch. There's only a small block within this module was used for DIO latch. That's this one. And this one connects to the address and data bus of the CPU, right? Actually to the data bus. So the rest of it is a display module. This is also subject of another video, so we'll not do this in detail. But this module is shared between, it has two purposes. One is implements the DIO latch, and the most of the module real estate is used for the display, right? Display controller and the matrix display. So DIO basically corresponds to, is implemented using one plug-in module, or actually half of a plug-in module sitting right there. Yeah? The other half of the module is used for the display. So this module has double purpose, yeah. So blue is the logic purpose and red is the display purpose. So that's that, right? Final one is the bridge module, and this the most fancy pants looking module in the CPU, and this is basically sitting between the between the USB bus to the PC and the address and data bus of the CPU. How all this works is again not subject of this video, but basically the PC implements the RAM and the ROM through a serial link, to a USB link, and this module bridges between USB on the PC side and address and data bus and control signals on the CPU side, sorry. But that's what this module does, it's a bridge. This is very subject to change, so let's call this version 1. And one of the plans is to make this a standalone module, so you don't need to actually implement a RAM and ROM here and have a nice interface and have some intelligence in this module. So to avoid the need to have a PC with a CPU all the time, so the CPU can run standalone. That's probably a good idea. So that's the final module, this one, right? Again, subject of another video, and that module is sitting right here. So and what's left is not much actually. It's a dumb baseboard. Put some feet on it for now. This might also change, maybe it becomes a bit smaller or something like that. So you see the filter caps at all of the inputs and buffer caps, and that's basically it. That's all this module does. Right, so that was basically it. Now again, the interface between the PC and the bridge module, and also the interface from the bridge module to the display module, may be interesting, is subject of another video. It's not described here. Now, thank you for watching, and I hope you get a better idea of what this CPU actually, what it looks like. So makes things a bit more clear maybe. Thanks for watching and have a nice day, and please watch the other videos. For more information see the video description at the bottom, and goodbye.